All right, so now we come to the topic of today's module, which is the Milky Way and other disk galaxies, or the Milky Way and other spiral galaxies. Here, of course, you see an, so to say, overview of, in this case, it's called the Milky Way anatomy. But it has the key components of most spiral galaxies, as we will see. We have the spiral arms here, of course. Now, we believe that in the Milky Way we have a bar, not all, a central bar, not all spiral galaxies have a central bar, as we probably are already aware. Here we see the disk edge on. Then we will talk quite a bit today also about the difference between the thin disk and the thick disk, as it's called. Yeah, here we have the bulge, as you can see prominently. We have a stellar halo, which contains a lot in our own Milky Way, dominated by these globular clusters, which we have mentioned before. And then, of course, we're all embedded in a huge dark matter halo. And here you sort of see a little bit the scales that we're dealing with there, right? We have the central supermassive black hole, which is also now a natural part of probably at least the vast majority of large galaxies. But we're not going to talk about that supermassive black hole today. That will come back in a later module. Today we're going to discuss our Milky Way first in the first block, a little bit on the motion of the stars, a little bit more on the structure, the disk I already mentioned, the thin and the thick disk, the bulge, the halo, the stellar and the dark matter, and a little bit on the gas, and then we're going to go to the rotation curve, of course. After that, in the second block, it's disk galaxies in general, spiral galaxies, properties, how do we characterize them, what are their surface brightnesses, and how do we characterize that, following up on the simple scaling exercise we just did. Then a little bit on the rotation curves of them, of course, and then the Tully-Fisher relation. I actually added a little bit on the thin and thick disk from some new JWST results here at the end as well. That's just a little addition there toward the end of today. So again, this is the anatomy of the Milky Way. As you can see, we sit here. As we already know, we have the bulge, we have the globular clusters, the disk, the stellar halo. Here is how it is viewed if we could ever see it from here in Belgium. Have anybody seen it at home? Like the white stripe that you can see if you go to a very dark place. But it's always cloudy. In Leuven, no, I'm joking. It's not all. Today is a very nice day. Has anybody seen it? You know, like the Milky Way stripe. Yeah, yeah. It is very beautiful when you get to a place in the world on a dark night where you can actually see it. It's quite stunning. Then, the faint band. Now, this we have also already mentioned. I will repeat it a little bit, because it is important, again, to keep in mind that it's very different for us to study the Milky Way than it is to study other spiral galaxies, simply because we sit in the middle. Yeah? So some things we can study in much greater detail, you know. And here I took the forest liking, which is popular, large scales of a forest while being lost inside it. That's not so trivial, right? You know, I like the analogy that, you know, I'm standing here inside this room, inside this building, which means that some details are trivial for me to deduce. I know exactly that Waipan is having a Guns N' Roses t-shirt, for example, for some reason. I also like Guns N' Roses. But on the other hand, I have no idea what the color of the roof of our building is. For that, to deduce that, it would be much easier for me if I could just step outside the building, go to our nearby building where we have our offices, right? And then just look on the roof. Then it would be trivial. Yeah? And I like that analogy to the analogy of observing the Milky Way versus observing other spiral galaxies. Here you see, according to the Gaia satellite, how we can very detailed now map out the motions of millions and millions and millions of stars in the Milky Way to get a dynamical picture. That's, of course, not possible for us to do in an external spiral galaxy far, far away from us in that level of detail. Again, here is just to illustrate you that the scales here, I normally say that you cannot really get used to them, but it's important to keep having them, try to have them in your head. Here I just try to illustrate, this is the size of the visible disk. The sun's position is 8,500 parsecs from the center. We'll see how far that is. That's very, very far away. But still, if you look at the disk, and then you take that disk out in the estimate of the dark halo that surrounds the Milky Way and galaxies in general, as we believe, you see that that's a factor of 10 larger. So that's huge. And then the spiral, the luminous component becomes really tiny. And this then again goes to the edges. That's not so easy to deduce where does a galaxy end and where does the next one begin, etc., etc. When we look, of course, only the visible parts, and we look out in the universe, we see them as these isolated islands. And they are for the luminous parts. But if we believe in this, our modern framework of that they are embedded in these huge dark matter halos, right? Then that's a different thing. Those, then of course, are much, much closer to each other in the sense there. But we cannot see them. We can gravitationally detect. Okay. So the orbits of the star in our Milky Way, in the disk, we orbit in the same direction. We have a little up and down motion. We have used this already. We deduced, we calculated already, we have like 220 kilometers per second as a rotation speed. And then we have a random velocity on top of that, which is on the order of 25 kilometers per second or so. Yeah, that's the sun. So we have dominated by rotational velocities, and that's the case for the disk. Yeah. Now, if you go to the bulge and the halo, this differs. The orbits of the stars, they have more random rotations. In the bulge, though, there is also rotating stars. However, the velocity, the dispersion, the random motion, is on the same order as the rotational speed. So that's very different than in the disk. So put it in this framework, in the bulge, they have the same order, but in the disk, then the dispersion is much, much smaller, factor of 10 smaller for the sun specifically, almost. Now, if you look and then at the disk specifically now, and the distribution of stars, here is where the majority of the stars are. This is the active star formation regions, as we know, in the disk. Then we can map out and we can count stars, and we come to the conclusion that they follow an exponential distribution. Okay, so if we now put this into some sort of coordinate system, where again we have the scale length here, that is the distance from the center in the disk. Yeah, this is the exponential that we have already encountered, r over the scale length hr, right? But then when we go vertically in the disk, we will also find roughly an exponential distribution of stars. Okay, now then we have another scale height associated with that, but actually the deduction here empirically is that we get much better fits to the counting here. Another properties if we superimpose two exponentials, one which is called then the thin disk and one which is then called the thick disk. Okay? So in general, these type of exponential distributions that we're dealing with, you can understand this via considering hydrostatic equilibrium, now in the C direction then, yeah, and associate your dynamical pressure in your Jeans equations, as we did in the last module. And then this dynamical pressure then has the velocity dispersion in it. Remember we discussed about this last week, yeah? And then the higher the velocity dispersion, yeah, the larger the scale height. It's essentially the velocity dispersions that says that. And that's also then the analogy to the terminology that we call a disk with a higher scale height that has a higher dynamical pressure, there's a higher velocity dispersion. We call that a hotter disk. Yeah? Remember this analogy with the hydrostatic equilibrium for a gaseous system, where we can associate this with the isothermal gas sound speed or the temperature of the gas. And just by analogy here, we can talk about a hot disk having a higher velocity dispersion and thus a larger scale height. Okay? This is an exercise for you to realize this. As you can see in this is like a best fitting formula. The majority of the star sits here in the thin disk. If we take a given distance here and then we go up vertically in the disk, the majority sits here and it is a minority that sits in the thick disk. Okay? Here you see one illustration of what I mean with this. You have basically two exponentials here. This is the star count versus the distance then, vertically. Yeah, and you can see that here you follow one distribution. So this would be the thin disk. This would be then the thick disk. Yeah, this is one of the classical papers in that realm. And you have the superposition then of the two exponential distributions to model this on this form here. Now the luminosity or the surface brightness in the thick disk is only about 10% of that of the thin disk. Now the inferred for the galaxy then scale heights here are very small for the thin disk, 300 parsec only. Yeah. The thick disk is higher, that's hence the name thick disk, right? 1,000 parsecs, and the scale length is on the order of 3,500 parsec. Again, to orient ourselves, we can think about that we sit 8.5 kiloparsecs roughly away from the center of the Milky Way. And we sit almost in the disk plane, a little bit higher, yeah? A few parsecs, 50 perhaps. The number density normalization that you can apply for the solar neighborhood, this we have had as well, is roughly 0.2 stars per cubic parsec. So again, you can see that in this sort of terminology, we have here that the thin disk is very cold, yeah, and the thick disk is a little bit hotter. This is a hotter disk than this. So the thick disk stars, they have higher velocity dispersions. Now, if we now look at the stellar populations of stars in the galaxy, we have, well, we're astronomers, so we like to classify them, give them names. We have population 1 stars, more metal rich. The sun is a population 1 star. Yeah, so later generations often formed a little bit later on. We have population 2 stars, which generally are then more metal poor. They're found primarily in globular clusters. Yeah, there we have normally very metal poor stars. They're older than, in the sense that they have not had time to undergo so much chemical enrichment. Yeah. And since they're very old, then they will also be highly skewed toward low massive stars. Because all the high massive stars that were formed in the early universe, they have of course died away long ago, right? So if you want a high massive star and you observe it, that's a POP1 star per definition, so to say, today in the Milky Way galaxy, because it has to have been formed within, say, the last 10 million years or so. Otherwise, it would have already died, right? Now, then we also have POP3 stars, and that's the hypothetical first stars that were metal-free. I say just almost metal-free because they have some lithium in them, right? But yeah, to all purposes, they are metal-free, only hydrogen and helium. They have not had time to have any metal enrichment. And yeah, we have already alluded to this because of the chemical enrichment process that takes place. Then we have an age difference, of course, that POP1 in general is younger than POP2, right? So you get an age-metallicity relation. And this age-metallicity relation is very strong, and it's very, very much used in extragalactic astronomy also to characterize this. Older stars have lower metallicities. Thick disk stars have lower metallicities than thin disk stars. Okay, let's think a little bit about what that might mean. Well, if we have thick disk stars of general, that they have lower metallicities than thin disk stars, it means that they are, on average, there is spread here obviously, they're formed earlier than the thin disk stars. Okay, because they have on average lower metallicities, meaning then that they have not had time to undergo as much chemical enrichment, thus they are older, formed earlier. Then it also makes sense that when you think about how this works, that the mass to light ratio for such older stellar populations are higher than the mass to light ratios for younger stellar populations. Yeah. So mass to light ratios we have already dealt with. It's on the order of 3 for thin disks, for the thin disk in general. Thick disk, it's a little bit higher, yeah, because they're generally older population than thin disk stars. And then we can again think about this in terms of how this works, yeah, because if this is dominated by stars, then we know from our stellar structure course that the luminosity goes essentially with the mass to a certain power. Yeah? 3 is a characteristic good number. But that means that if you have a 10 solar mass star, say, yeah, then that shines with a much higher luminosity than 10 times the sun, because it goes with the cube. Right? So 1,000, yeah, in this scaling relation. Yeah? If you have 100 solar mass star, that would shine according to this scaling relation with 1,000,000 times of the sun, but it's only 100 times as more massive. This means that the mass to luminosity ratio is much smaller for high mass stars than for low mass stars. Okay, so that's part number 1 here. The part number 2 then, to keep our logic in place, hopefully. You have to interrupt me now if I say something wrong and I get this twisted or something. Yeah. Then the second part then that connects to this is of course that those high mass stars are also those, as we have said, that live shorter. A typical high mass star perhaps lives 1 million or 10 million years, whereas a low mass star like the sun lives 10 billion years, yeah, and an even lower mass star like the sun, none of them would have actually died yet. okay, become white dwarf. That's what we see in globular clusters. So that means that an older stellar population then, the massive stars, they have already died away. There aren't any around unless they are continuously being formed, okay? And that means that the mass to light ratio goes up, right? So the older the stellar population, the higher the mass to light ratio becomes, and vice versa. And this is how you can use this to learn about the properties. All right, so this metal enrichment then that I have alluded to, how does it actually occur? Well, there are two main processes that we can keep in our head to try to understand some of these features that we see. And that is that, okay, metal enrichment, it happens via supernovae, where, you know, a supernovae from your other courses, it explodes. The luminosities of the supernova can rival almost that of the whole galaxy for a very short amount of time. And they're spitting out the material from whatever went supernova into the interstellar medium. And that material then can be used to form the next generation of star. And that's how we get the metal enrichment, as we know from our basic courses in astronomy. Now, two different sorts, we can call it, important to keep in mind there. Massive star explosions. Massive star explosions, we already discussed, massive stars live short. They are thus immediate on a cosmological timescale. They're happening now, directly, right? And they are the supernova category 2, 1b, 1c, depending on if you have hydrogen or not, essentially, and others, and helium. And the enrichment properties here has to do with what sets the nuclear, how the nuclear burning in the last phases of the massive star evolution cycle goes before you go supernova. Okay, and that's I referred to you to your course in stellar structure and evolution for this. Now, what is important for us here is that so-called alpha elements dominates. The alpha elements are, you know, the factor 4. So oxygen, magnesium, etc., etc. That has to do with the nuclear processes involved here. Now, the second is the so-called white dwarf supernova, or the type 1a, if you will, and that's explosions of white dwarfs exceeding the Chandrasekhar limit. The Chandrasekhar limit is this fundamental mass limit that once you have, and that you can have, well, you can have it from, say, accreting material from another star, a binary star system, and then you accrete material until the white dwarf exceeds the Chandrasekhar limit and then explode. Yeah, you could also have it from merging to white dwarf, for example. Yeah? Regardless of what, you need to produce a white dwarf in order to get the type 9a supernova, we believe. Yeah? Now, to produce a white dwarf, that's from the low mass star end of the evolution, right? So, in order to produce a white dwarf, you need some time. You need more time than to explode the metal core. And that's why we talk that this is a delayed reaction. It doesn't happen in the beginning. You need some time in order for the stars to, you know, die out and become white dwarfs. Only then can you have the type 1a supernova afterwards. And in terms of the chemical enrichment, it's very different because this is highly iron dominated. Here we have the alpha elements, and here we have the iron. Yeah? So we have a delayed reaction, and we have iron dominated. Now, I should mention, of course, these white dwarf supernova. They're also very famous as cosmic standard candles. And this, of course, we'll come back to during the later parts in our course. Now we're just talking about the role as chemical enrichers, though. So here you see an illustration of this. This is metal enrichment then via supernova. You have your core collapse supernova only in the star-forming galaxies because you need massive stars around. So if you don't have any star, if your galaxy is not star-forming, so for example the elliptical galaxies, then you won't have any core collapse supernova going on. Yeah, there aren't any massive stars there. It's an immediate reaction. But the type 1a, though, that can happen in all sorts of galaxies. That just requires white dwarfs, right? So it's a delayed, so you have to wait, but then it starts to happen, and it can happen in all sorts of galaxies, right? You get an age-metallicity relation here. So, for example, then, if you look iron, the iron content here, that can be used as a tracer, since iron is ejected into the ISM primarily by this type 1a, right? And then you can compare this to your alpha elements, oxygen, magnesium, since they are alpha element, produced mainly in core collapse. So what should you have then? Well, you should have that in the beginning, the enrichers are via the immediate, that is the massive star collapse, and that's alpha enricher. So the alpha over iron content should be high. Then as time goes by, more and more die out, perhaps we even cease with star formation, and the enrichment via the type 1a supernova will become more and more prominent until the time where we have no active star formation anymore, thus no type 1 or massive star collapse supernova, and therefore only enrichment via this. That is to say that over time the alpha over iron ratio, as plotted here in the image, should go down. That should also be then reflected in the stellar populations, depending on what you are. And you see this here, right? That typically the thick disk stars, they have, for given metallicity here, higher alpha over iron content than the thin disk stars. And this is what I mean, that this is then an indication of, on average, an older stellar population. Okay? Not as many type 1a has had time to go off and bring this ratio down as compared to the thin disk stars. Yes, so put it in a short sentence. Most of the thick disk, and this also holds for the bulge, I took the thick disk here as an example, stars formed before the type 1a supernova explosions could occur. Therefore, the alpha over iron is enhanced. All right, so if we summarize now the structure of the galaxy, we had an exponential distribution of stellar density. We can understand this via the dynamical pressure, velocity dispersion, analogous to temperature in the gas dynamics. So when you read literature on this, you often hear about hot disks and cool disks, and hopefully this is now clear, that type of terminology. Velocity dispersion is lower in younger stellar populations. They have smaller scale. We have a thin and a thick disk. We have an age-metallicity relation. Now, the origin of the thick disk is still an active area of research, very active area of research, I should say, where we have different suggestions and different theories for different models for this, where one is the migration of stars, that is that you increase, you have small tugs, so you increase the velocity dispersion of the stars over time, which means that then, yeah, you increase the velocity dispersion, the scale height gets larger and larger, the disk gets hotter. Huh? Okay, now another is the opposite, and that is that it's an early hot formation scenario. That is that you form in an early time, perhaps in a very turbulent star formation sites, such that you form a hot disk first, and that then settles down into a more quiescent disk. Okay, and then we also have the role of capture of stars from nearby dwarf galaxies. As we know, for example, our Milky Way is currently eating the Sagittarius galaxy, right? So we're capturing stars from out, and perhaps we capture those, and those can then lead to higher velocity dispersions. They settle into the disk, but with higher velocity dispersions because of mergers. And there isn't, I guess, any clear consensus on this. I will actually illustrate at the very end of the lecture today some new some new web results of investigating disks at very far distances, up to redshifts of at least 3, where they essentially argue for an early hot formation scenario. Yeah. All right, the bulge, next part. Strong extinction, so we have to go to the infrared. We have already discussed this. Remember that, for example, in the famous results that gave the Nobel Prize, that was essentially measuring stellar motions close to the galactic center, and from those stellar motions, applied Kepler's law, more or less, and deduced that there must be a supermassive black hole or a compact object sitting of a very large mass sitting in the center of the Milky Way. But since we have such strong extinction there, you had to go to the infrared or even radio in order to make those detections, which made the observations very challenging there. Now, here in the bulge, we're talking about the scale length of 1,000, the scale out on 400. So this is a flattened. So it's a bulge, but it's flattened. Yeah, you can see it. It rotates like the disk, but slower. I already mentioned that the velocity dispersion is on the same order as the rotation here. Yes, the mass to light ratio indeed is a bit higher than in the disk, meaning older stellar population, according to the arguments that we just discussed. Now, instead of fitting an exponential distribution as is normally done for the disk, and which we did in the exercise this morning, a de Vaucouleurs law is better for these type of systems, as we already said in the introductory parts. Effective radius of 700 roughly. Now, the stellar halo then, there are field stars, yes, but they're mostly concentrated here in about 150 globular clusters. And there are thousands of stars packed within 20 or so parsecs. And remember that we already made the distinction between a dwarf galaxy and a globular cluster, where globular cluster, they might have similar luminosities, for example, but a globular cluster is typically much more tightly packed. Yeah. And for our dynamic session that we did last week, in globular clusters, remember we did these estimates, and we basically shown that luckily for us, you know, the likelihood that the sun will collide with another star within a Hubble time is very low. But in globular clusters, though, since the stars are so tightly packed, this is no longer true. There, particularly toward the center, these type of collisions can occur more frequently. So I encourage you to try to make some estimates on that. Similarly then, another important phenomena for globular cluster evolution has to do with this evaporation effect that we also discussed. That is, when we looked at we took the isothermal sphere models, right? But then we said, okay, but it basically continues 1 over r squared, so mass becomes infinite the mass becomes infinite, right? And then we said that what physically happens is that you need to truncate the velocity distribution, right? And you need to truncate this velocity distribution at essentially the escape speed of the system. Because if you have stars, in this case, that exceed, the random velocities exceed the escape speed of the system, they will be expelled. That happens here, and then we talk about, for example, runaway stars from clusters, etc. Yeah. So globular clusters can also evaporate in that sense. Here are now, this is for the stellar halo in large, the number of populations, and again, if you want to fit something, a de Vaucouleurs law here is again reasonable. Then the dark matter halo. We already alluded to the sizes here. Here again, this is an artist's illustration, right? But this would be the size of the visible disk, and this is the dark matter halo. The radius at least above 100 kiloparsec. We don't really know how far out it really goes. 90% of the Milky Way mass inside the 100 kiloparsecs. We had something like 10 to the 11, right, inside the sun's orbit. We calculated that. So this would be on the order of 10 to the 12 then, solar masses. Yeah, and the density profile seemed to follow 1 over r squared out to very large radii. And recall then again the isothermal sphere, right? That's indirect, can also be learned from studying the rotation curves, as we have said. Now, the content of this dark matter halo is unknown, as is also familiar to us. There has been, for example, a microlensing project for detecting so-called massive compact halo objects. So that would be like, I don't know, white dwarfs, etc., that we cannot see because they simply, they're ordinary baryonic matter, but it's not in a luminous form of, say, stars that we can actually detect it, right? So there has been then microlensing to try to see whether the halo could consist of such baryonic massive compact halo objects. But the main results from those is that the majority of mass is actually likely to be in non-baryonic form, okay? I refer here, if you want more details of this, to Peter Schneider's book, where he discusses this in 2.5. Gravitational lensing is, of course, his speciality, so this is something that is done in a very good and detailed way in his textbook. Now, here is a dark matter simulation. So this is a simulation now where they have very nice colors, right? But it's actually dark matter particles here. Illustrating this. So this is an N-body simulation, Aquarius simulation, which is follow-up, you may say, to the famous Millennium simulations of these type of dark matters, illustrating again this halo from Volker Springel's group. Now, next component, the diffuse gas. We will mainly concern ourselves now with two parts, H2 and H1 region. So H2 region, ionized hydrogen, we know this from radiative process course, associated with active star formation, of course, because it's believed that you have the massive stars that shines and they ionize their surroundings, blowing these ionized bubbles, or the H2 regions. So you need massive stars, thus you need active star formation, according to the arguments before. Therefore, you find them in the spiral arms mostly. Ionized gas metal line emission here is often used to determine extragalactic metallicities. So you look at this ionized gas, and then you look at observations of the metal lines in them, and from that you try to deduce the abundance of the galaxy. That's a very common method to infer galactic chemical abundances. Now the H1 regions, that's the neutral gas with, and that's observed to much larger distances than the H2 gas. That is not just in star regions, right? Up to, say, 25 kiloparsecs in the Milky Way, scale height around 160. Dightly, you can see a little bit here. And of course, the most famous neutral gas, neutral hydrogen gas diagnostic is the 21 centimeter line. Again, which we talked about a lot in the radiative processes course. Here, in this context, today, it is used to infer the rotation curves, as we have already alluded to. Now, I should say the 21 centimeter line, though, is used in a lot of areas of extragalactic astronomy, right? Even in the context of trying to map up, say, the reionization of the universe. Now, the total amount, though, in the gas as compared to the stars is actually small. It's 5 to 10%. So the vast majority of the mass sits in the stars in this case, if you talk about the luminous mass. And here is the little bit of an overview. This is repetition. So I refer to my radiative processes lectures and the corresponding there. For this is the hydrogen 21 centimeter line. We know, though, that it has a very low, of course, Stern probability. But since there's so much hydrogen around, we actually still get some detections. I inserted a little bit of an exercise estimate that we can do to remind ourselves of these properties until next week. Okay. Now, here is the rotation curve. This I showed during the first. This is actually from an old group assignment in this course, where they actually did take some observational data here, downloaded it, and then made a model of, well, in this case, we have some baryonic matter disk. We have a bulge, the supermassive black hole. You don't really see it here. And then you have the dark matter halo. And of course, the key point from this is the observed rotation curve, yeah, to high radii in the Milky Way, so far out, yeah. We're about there at 220 roughly, yeah. And if you only have the disk, yeah, you see that it would be much lower and it would have a different form. So in order to fit the rotation curve, a dark matter halo has to be superimposed. Otherwise, we rotate too fast. In this particular case, they used one of these Navarro-Frank White analytic dark matter halo density distributions in order to fit the observed rotation curve. Okay, so this is sort of the key illustration why the dark matter halo is needed to fit the rotation curves of spiral galaxies. In this case, then, of course, the Milky Way. So, before we take a break, I wanted to just, because I come back to this, but I think it is important, since now when we're going to discuss galaxies, and then we're going to go up to galaxy clusters and even, that we remind ourselves of the scales that we're talking about here. If we have the approximate diameter of the visible Milky Way, yeah, we're talking about 20 kiloparsecs, because that's the astronomical units we have to work. But if we talk about that in our everyday units, in kilometers, do we think it's a billion, 100,000, 10 trillion, 1 million trillion? We think it's A, B, C, D? Yes. I mean, I wouldn't, of course, I put the most extreme. Yeah. This is just to remind you again that it is useful. This is the visible disk. Then the dark halo, in that sense, would be 10 times larger than this. And this is a number which I've done this for many years now, but it's just, to me, it's impossible to get used to just how vast the scales we're talking about. And now we're just talking about the galaxy itself. We're not even talking about galaxy clusters or large-scale structures. This is the galaxy itself that we're talking about now. So it's just a useful reminder, at least I find it useful when you are studying or doing astronomy for a living. Then it's just mind-blowing, let's just say. All right, we'll take a short break.